In this video, we're going to talk about how to calculate the pH of a buffered solution and what's really happening during the titration. Well, pH of buffered solutions are controlled by the weak acid and its conjugate ion concentration. And the way we go about setting up determining final concentrations involving equilibrium involve setting up ice tables. So here we've got our lactic acid and sodium lactate solution from the previous problem, and what we're going to go through and do is set up an ice table to determine what the pH of the solution is. So you can see I've got my initial concentrations plugged in there. The change is just a single component of X, since everything is a 1-to-1 ratio from the balanced chemical equation. And at equilibrium, we have our modified concentrations involving increasing or decreasing the value of X. Once we have our equilibrium concentrations determined, we can plug that into our good old equilibrium expression and solve for X. In this case, the pH of the solution would be expected to be around 3.77, making it an acidic solution and falling somewhere near the range of the pKa for the solution. Now, I don't know about you, but I'm kind of sick and tired of solving for a quadratic equation every time that we have to do an ice table. And so what we're going to introduce is a new way of calculating pH for buffered solutions that doesn't require quadratic. Now, you have to remember this only works for buffered solutions and not every solution. So here it is. It's known as the Henderson-Hasselbalch equation. And the way it works is that the pH of the solution is equal to the pKa plus the log of the ratio of the conjugate ion to the weak acid concentration. And that's it. It's a plug and chug problem. No ice tables needed, no quadratic equation needed. It's a really nice and elegant equation which gets us the same pH we would if we were going through and solving for an ice table. Now, Henderson-Hasselbalch is a very useful equation in biochemistry, and perhaps some people may have been jealous of the Henderson-Hasselbalch equation. For example, this guy has a different opinion on what the equation should be called, but we stuck with Henderson-Hasselbalch. So if we go back and we solve for the same problem again using the Henderson-Hasselbalch equation, we can see that the pH works out to be the same. The pH is equal to the pKa, so the negative log of 1.4 times 10 to the negative fourth is the same as 3.85. And then we have the log of the ratio of the two concentrations, the 0.1 and the 0.12. Now it's important to note it's the ratio of those weak acid and conjugate ion concentration that controls the pH of the solution. Not the actual molarity itself, but the ratio of the molarity of those two things. That's where the adjustment of pH comes. Now, there is an alternative form to the Henderson-Hasselbalch equation dealing with bases. However, we're going to try and avoid that when possible. But I thought I'd just show you the equation just in case you encounter it in your future careers. Now, titration is something we've done in lab, and that's been predominantly done with unknown solutions, and we're just trying to find the endpoint or the equivalence point. That is, when the moles of something equals the moles of something else. Or in lab, you've probably done this as the moles of acid equals the moles of base. Well, titration can be done using a pH meter, and we can use or track the pH of a solution as we perform the titration. The question then remains, what is happening during the titration? That is, when we're not at the equivalence point. Well, when we have a strong acid and a strong base being added to each other during titration, we can find that the pH of the solution is controlled entirely by the strong acid. That is, when we're adding a strong base to a strong acid, the amount of acid that is present controls the pH. And when we get to the equivalence point, that is the point where the moles of acid is equal to the moles of base, we find that the pH is 7. Now this is only true when a strong acid is being added to a strong base or vice versa. For all other situations, the pH will not be 7 at the equivalence point. But we can see from the graph that as sodium hydroxide is added, the pH slowly increases and then jumps very dramatically at the equivalence point. And above the equivalence point, the pH of the solution is controlled by the base. With a weak acid, that's a very different story. Strong base being titrated with a strong acid, we find that the pH curve looks just the opposite. That is, the base controls the pH of solution prior to the equivalence point, and that the acid controls the pH of solution after the equivalence point. But again, the equivalence point is where the moles of acid equals the moles of base. And this has typically been seen in lab when you have your color change of solution, whether it's going from colorless to pink when you've used phenolphthalein, or perhaps going pink to colorless. Weak acid-base titrations look slightly different. When we do a weak acid titration with a strong base, we must go about solving for the pH in a number of different ways. Looking at the plot to the right, we can see that there's an initial jump in pH when the titration starts, and then once we start the titration, we get into this nice buffered region where the pH remains relatively constant before arriving at the equivalence point where the moles of acid is equal to the moles of base. Note at this point that the moles of acid and moles of base are equal to a pH above 7. In fact, in this one it looks like somewhere around 8.3, 8.4. You can find the pH of the solution in the buffered region, that is, after you've started the titration but before you hit the equivalence point, by using the Henderson-Hasselbalch equation. At the equivalence point, however, when you go to find the pH, you're going to find that the Henderson-Hasselbalch equation fails because you have no acid concentration. That is, all the acid has been used up, but you have the conjugate base present, that is, the common ion of the acid floating around in solution. And so you'll have to use an ice table to determine the pH both at the equivalence point and initially. After the equivalence point, the base takes over the pH of solution, and presumably you're using a strong base, so there's no longer any equilibrium involved, and so you can get away with using the concentration of the base after the equivalence point to find the pH. So different weak acids have different equilibrium constants, and what we find is that depending upon the equilibrium constant, the curve will have a different shape. Now, you can see here I've got 5 different acid-base titrations, and that we can see as the Ka value diminishes or gets smaller, that curve in the middle during the buffering region moves up and up and up on the pH plot. So we find that all these weak acids start below a pH of 7 initially. During the course of the titration, the buffered region can vary depending upon what the acid dissociation constant is. And at the equivalence point, we will find that each one of these acids has an equivalence point above a pH of 7. Remember, it's only the strong acid that will have a pH of 7 at the equivalence point. Now, some acids have more than one acidic proton. These are known as polyprotic acids. They have 2, 3, or even 4 acidic protons, and each one of those protons has its own unique equilibrium constant. That is, it has multiple Ka values depending upon how many protons can be removed. This here is an example of phosphoric acid and its titration with a strong base. And what we can see is that there are a number of different equivalence points depending upon which proton is being removed. In fact, Here we see 2 of the 3 acid dissociation constants for phosphoric acid. So don't think that every acid has just one equivalence point. If there are multiple protons, then there are multiple equivalence points, each one controlled by the Ka or pKa of that particular proton.